Hi everyone, let's dive into the session on number systems. We shall see the basic number systems and their conversions. Number systems are standardized ways of representing data or numbers. These are the different number systems that we are going to discuss today, namely the decimal number system, binary number system, octal, and hexadecimal. Now let's see each one of these in detail. The decimal number system. This is the number system we all are familiar with. This system contains 10 unique symbols called the digits that represent the digits or fingers of a human because a human started counting with their 10 fingers. Since counting in decimal involves 10 symbols, 0 to 9, we say its base or radix is 10. However, its base is not included in its symbols. This is applicable for all the other number systems we are going to discuss. These number systems are positional weighted systems, which means that the value attached to a symbol depends on its location with respect to the decimal point. That's exactly what we refer to as the place value that we have studied during our school days. In the decimal system, any number, be it the integer, fraction, or mixed, of any magnitude can be represented by the use of these 10 symbols only. Consider a decimal number as shown. The number is 87,541. Here, 8 is the MSD or the most significant digit. The highest positional weight or the highest place value is associated with the most significant digit. In this case, the highest positional weight is 10 raised to 4 or 10,000. The lowest positional weight is 10 raised to 0 or 1 or units, and this is associated with the LSD or the least significant digit. Other positional weights or the place values are 10 raised to 3 or thousands, 10 raised to 2 or hundreds, 10 raised to 1 or the tens. The phase values are the digits itself, namely 8, 7, 5, 4, and 1. The binary number system. Just like the decimal number system, this is also a positional weighted system. As we all know, it has two symbols, namely 0 and 1, and its base is 2. And a binary digit is called a bit. Just as a decimal point separates integer and fraction parts, in this case, the counterpart is the binary point, which separates the integer and the fraction parts. Consider a binary number 10101. In this case, the rightmost bit has the least positional weight or the place value of 2 raised to 0. It is the lowest significant bit or the least significant bit or LSB. Since 2 raised to 0 is equal to 1, it corresponds to the units column. The bit column to the left has a weight of 2 raised to 1 is equal to 2, and it is the 2's column. Next is a 2 raised to 2 is equal to 4, and hence it is called the 4's column. Next is the 8's column, and so on. The leftmost bit has the highest positional weight and is referred to as the MSB or the most significant bit. Here, MSB is in 2 raised to 4, which is equal to 16. That is, it is in the 16's column. The octal number system was extensively used by early mini computers. It is also a position weighted system with the base or the radix equal to 8, and it has 8 independent symbols from 0 to 7. The base itself is not a symbol. This means that the base, which is 8, is not included in the symbol list. The hexadecimal number system. This is another positional weighted system with base equal to 16. It has 16 independent symbols ranging from 0 to 9 and from A to F. The hexadecimal counting sequence. Here we can see that the hexadecimal numbers from 0 to 9 is same as that in the decimal counting. After 9, the hex system counts from A to F instead of its decimal equivalent of 10 to 15. After F, the hexadecimal or the hex sequence continues from 10. The digital circuits and systems work with the binary numbers. These binary numbers do not always represent a numerical quantity. It can represent the numbers corresponding to a memory address or an instruction code, or even a group of bits representing the status of internal or external devices. In computer related operations, it is common to come across binary numbers of even 64 bits length. These numbers are fine for machines but are too lengthy to be handled by humans. So, there is a need to represent the binary numbers concisely. In such cases, the numbers need to be converted from one form to another. First, we shall see the conversions to the number system we all are familiar with, which is the decimal number system. Let us now discuss the binary to decimal conversions. For conversions to the decimal number system, we can use the positional weights method. In this method, each binary digit is multiplied by its position weights, and the product terms so obtained are added together to get the decimal counterpart. Let us see this with the help of an example. Consider a binary number 10101. The rightmost bit, that is 1, is the LSB, and its positional weight is 2 raised to 0 as shown. Likewise, the leftmost bit is the MSB, and its weight is 2 raised to 4. Next, we obtain the product terms by multiplying each bit by its corresponding weight. Here we multiply the MSB with its corresponding weight, that is 1 into 2 raised to 4. Similarly, 0 into 2 raised to 3, 1 into 2 raised to 2, 0 into 2 raised to 1, and 1 into 2 raised to 0. These are the product terms. Next step is addition. That is, we add all these product terms obtained in this step to get the sum. So here we get 1 into 16 because 2 raised to 4 is 16. Next, 2 cube is 8. So 0 into 8 plus 1 into 4 plus 0 into 2 raised to 1, which is 0 into 2, plus 1 into 2 raised to 0, which is 1 into 1. So adding all this, we get 16 plus 4 plus 1, which is equal to 21. Let's now see the conversion of a mixed binary number 101101.101 to decimal. It has the integer part 101101 and the fractional part 101. Starting from the binary point to the left, the bits are assigned the weights 2 raised to 0, 2 raised to 1, 2 raised to 2, and so on. On the other hand, starting from the binary point to the right, the bits are assigned negative powers of 2. So here 2 raised to minus 1 is assigned to this particular bit, and to 0 it is assigned 2 raised to minus 2 and 2 raised to minus 3. As before, we get the product terms by multiplying each of the bit with its corresponding positional weight. So here we get 1 into 2 raised to 5, 0 into 2 raised to 4, 1 into 2 cube, 1 into 2 square, 0 into 2 raised to 1, 1 into 2 raised to 0, 1 into 2 raised to minus 1, 0 into 2 raised to minus 2, and 1 into 2 raised to minus 3. In the next step, we add all these product terms. So we have 1 into 2 raised to 5 plus 0 into 2 raised to 4 plus 1 into 2 raised to 3. Because we add all these product terms and we get like this. Next, we put the values for each of the terms. That is like 2 raised to 5 is 32, 2 raised to 4 is 16, 2 cube is 8, 2 square being 4, 2 raised to 1 is 2, and so on. While in this case, 2 raised to minus 1 is 1 by 2, 2 raised to minus 2 is 1 by 4, and 2 raised to minus 3 is 1 by 8. So on adding all these, we get the decimal counterpart as 45.625. For any conversion to decimal, we can generalize the algorithm like this. That is, multiply each face value by the corresponding place value and then get the sum. Here the face value means the digits. The place values are powers of 2 for binary since its base is 2. For octal, the place values are powers of 8, and for hexadecimal, the place values are powers of 16. Now let us discuss the octal to decimal conversion. Consider the octal number 524.67. We shall see its conversion to decimal. The weights are assigned from the octal point. The weights are 8 raised to 0, 8 raised to 1, and 8 square. To the right of the octal point, we have the negative powers, namely 8 raised to minus 1 and 8 raised to minus 2. As for binary, in the first step, we obtain the product terms and then we get the sum. So the product terms are obtained by multiplying the octal digits with its corresponding positional weight. So here we have 5 into 8 square, 2 into 8 raised to 1, and 4 into 8 raised to 0. For the negative powers, we do 6 into 8 raised to minus 1, 7 into 8 raised to minus 2. And in the next step, we perform addition of all these product terms. Then we substitute the values for each of the power terms. That is 8 square is 64, 8 raised to 1 is 8, 8 raised to 0 is 1, 8 raised to minus 1 is 1 by 8, 8 raised to minus 2 is 1 by 64. After multiplying, we get 5 into 64 is 320, 2 eights are 16, 4 ones are 4, 6 by 8 is 0.75, and 7 by 64 is 0.109. Taking all these sum, we get the decimal counterpart as 340.859. Next is the hexadecimal to decimal conversion. The hex number in this case is A14.56. The weights from the left of the hex points are 16 raised to 0, 16 raised to 1, and 16 square. To the right of the hex point, there are negative powers, namely 16 raised to minus 1 and 16 raised to minus 2. Here we are taking the positional weights as powers of 16 because the base of the hexadecimal is 16. Next, we obtain the product terms by multiplying each of the hex digit with its corresponding positional weight. So we get A into 16 square, 1 into 16 raised to 1, 4 into 16 raised to 0, 5 into 16 raised to minus 1, and 6 into 16 raised to minus 2. In the next step, we take the sum of all these product terms. So here you can note that the decimal counterpart of A is 10. So we get 10 into 16 square plus 1 into 16 raised to 1 and so on. That is, we add all these product terms together. Now we substitute the values for each of the power terms. That is 16 square is 256, 16 raised to 1 is 16, 16 raised to 0 is 1, and 16 raised to minus 1, we take it as 1 by 16, and 16 raised to minus 2 is 1 by 16 square, which is 1 by 256. So when we do the multiplication and taking the sum, we get the decimal counterpart as 2580.336. Let us now see the conversions from the decimal number system. First, decimal to binary. We convert a decimal number to binary by the double-double method. In this method, the given decimal integer is divided successively till the quotient is 0 or till the quotient is less than the base 2. And the remainders are read from bottom to top or in the reverse order to get the required binary equivalent. Let us see this with the help of an example. We shall try to get the binary equivalent of the decimal number 21. So we divide 21 by 2. We know the quotient is 10 and the remainder is 1. So here quotient is 10 and remainder is 1. Similarly, we do 10 by 2. We get 5. Remainder is 0. We again divide 5 by 2. This case the quotient is 2 and the remainder is 1. Next we again divide this 2 by the base 2. So we get the quotient 1 and remainder being 0. The further division of 1 by the base 2 is not possible, so we stop here. Now the final remainder 1 is the MSB, and we read the remainders from bottom to top to get the binary equivalent. That is 10101. What we saw was the conversion for an integer 21. Let us see how to do the double-double method for fractional or mixed numbers. As before, for the integer part, successive division of given decimal integer by 2 is done, and the remainders are read in the reverse order to get the equivalent binary integer. But for the fractional part, the procedure is kind of inverse of the integer part. So in this, we do successive multiplication instead of the division. Let us understand this with the help of an example. So here we are trying to convert the decimal number, which is a mixed number 21.625, to its binary counterpart. So first of all, we take the integer 21 and divide it successively by the base 2 of the binary system. And we have seen this previously. Next, we take the fractional part 0.625. For that, what we do is we successively multiply by the base 2. So 0.625 into 2 is 1.25, and we take the integer part of the product to the right side. We again multiply the fractional part of the product obtained by 2, and we get 0.50. In this case, the integer is 0, and we take again do multiplication of this 0.50 by 2. So the product obtained is 1, because 0.5 into 2 is 1, and we take that 1 to the right hand side. Now this one is the MSB, and we read it from top to bottom, which is inverse of this order. The binary equivalent of the integer part is 10101, which we got by putting it in this order. Whereas the binary equivalent of the fractional part is 101, which we obtain by reading it in this direction. In general, for the conversion from decimal, we divide the integer part with the new base and collect the remainders in reverse order. On the other hand, for the decimal part, we multiply it with the new base, and the integer part of the result or the product is collected in the normal order. For the conversion from decimal to octal, we use the octal double method, which is similar to the double double method for the binary numbers. Let us see the conversion of decimal number 289.625 to its octal counterpart. Here the integer part 289 is divided successively by the base 8 of the octal number system, and the remainders are read in the reverse order. On the other hand, the fraction part is multiplied by 8, and the integer part of the product is read in normal order. So here we divide 289 by 8, and we get the quotient as 36 and the remainder as 1. We again divide this 36 by 8, and we get the quotient 4 and remainder 4. We stop the division here because this quotient obtained 4 is less than the base 8. So we get the octal equivalent of the integer 289 as 441. For the fractional part, we multiply 0.625 by 8 and we get the value as 5.00, and the integer part of the product 5 is taken to the right side, and that is the octal counterpart of the fractional part 0.625. The hexadecimal method is used for decimal to hexadecimal conversion. Let me explain this with an example. We shall see the conversion of the decimal number 289.625 to its hexadecimal counterpart. The integer part 289 is divided by 16 until the quotient is less than the base 16, and the remainders in the reverse order will give the hexadecimal equivalent. So here the integer part 289 is divided by 16, we get the quotient 18 and the remainder 1. Again this 18 is divided by base 16 to get the quotient 1 and remainder 2. We stop the division here because this quotient 1 is less than 16, and the remainders when read in the reverse order will give the hexadecimal equivalent of the integer part. The fractional part 0.625 is multiplied by 16 and we get 10.00, and the integer part of this product, which is 10, is moved to the right hand side, and this 10 in decimal is A in hexadecimal. See here, 10 in decimal is A in hexadecimal. So we have the hexadecimal equivalent as 121.8. Next is the conversion to the binary number system from octal and hexadecimal number systems. Since 8 is equal to 2 cube, every 3-bit group of binary can be represented by an octal digit. This is the octal to binary table, which shows the octal digit and its 3-bit binary counterpart. So 0 is represented by 000, and 7 is represented by 111. Here bitwise addition is performed and each binary group is incremented by 1 to get this table. For octal to binary conversion, each octal digit is replaced by its corresponding 3-bit binary counterpart. For example, consider the conversion of octal number 5760.1423 to the binary number system. Here, each octal digit is represented by its 3-bit binary equivalent. Say, for example, see here 5 is replaced by its 3-bit binary representation, which is 101, and 7 is replaced by 111. 6, its 3-bit binary representation is 110. Similarly, for 0, its 3-bit binary is 000. For 1, the 3-bit binary representation is 001. For 4, it is 100. For 2, it is 010. For 3, it is 011. These 3-bit combinations are joined together to get the final binary counterpart. Next is the conversion from the hexadecimal number system to binary number system. Here, the base of the hexadecimal number system is 16, and the 16 is equal to 2 raised to 4. So, every 4-bit binary combination can be represented by one hexadecimal digit. Such 4-bit group is called a nibble. This is the hexadecimal to binary conversion table, which shows the hex digits and their 4-bit binary counterpart. For hexadecimal to binary conversion, each hex digit is replaced by its 4-bit binary equivalent. Let us see the conversion of the hexadecimal number A29.C9 to its binary counterpart. Each of the hex digit is replaced by its 4-bit binary equivalent or the nibble. So A, which is the hex number, its decimal equivalent is 10, and its 4-bit binary equivalent is 1010. And for 2, it is 0010. For 9, it is 1001. You can refer to the hex to binary table for your reference. And C is replaced by 1100, 9 is replaced by 1001. Joining all these 4-bit binary equivalent from left to right, you get the binary equivalent of the given number A29.C9 as this. Now let's try to convert the binary numbers to other forms. First, consider the binary to octal conversions. For this, form groups of 3 starting from the binary point to the left and to the right. And then each of these groups is replaced by the corresponding octal number as shown in this table. Consider the binary number 110.111.1011. You shall see the conversion of this number to octal. So we are grouping this number from the binary point. In a grouping by 3 from the left of the binary point, we get numbers 111 and 110. For the fractional part, we group the numbers from the right of the binary point like this. So we get 101 and you get an additional 1 here. So you add 2 zeros to that one to get the 3-bit group. Next, we convert the 3-bit binary to its octal equivalent. So 110 is 6, 111 is 7, 101 is 5 and 100 is 4. You can refer to this table to convert the 3-bit binary to its octal equivalent. Finally, you get the octal number as 67.54. For binary to hexadecimal conversion, form groups of 4 starting from the binary point to the left and to the right. Then each of these groups are replaced by the corresponding hexadecimal equivalent. Consider the binary number 00110111.1011. We shall see the conversion of this binary number to hexadecimal. For this, we start grouping from the left of the binary point. So we get like this, and the nibbles are 0011 and 0111. Then for the fractional part, we group towards the right of the binary point and we get the nibble 1011. You can refer to this table to get the hexadecimal equivalent of the 4-bit binary. From the conversion table, the hex equivalent of this nibble is 3. For this, it is 7 and B. Joining all these together, you get the hex number as 37 point B. Finally, we have the indirect conversions, that is the conversion from hexadecimal to octal and conversion from octal to hexadecimal. In these cases, the binary number system acts as a bridge. For the conversion from hexadecimal to octal, perform the hexadecimal to binary conversion that we have seen earlier. That is, by replacing each hex digit by its 4-bit binary equivalent. The binary number so obtained is then converted to octal after forming groups of 3. Let me explain this with an example. So here we are trying to convert the hex number A29.C9 to octal. So what we do is we replace each of the hex digit with its 4-bit binary equivalent. Joining all these, we get the binary number as shown here. Next, we have to convert the binary number obtained here to its octal counterpart. For that, what we do is we make groups of 3 as discussed earlier. So we start from the binary point here, and towards the left, we start dividing into groups of 3 like this. So we get the corresponding 3-bit representation like this: 101, 000, 101, and 001. Now for the fractional parts, we start dividing into groups of 3 from the right of the binary point. Here we have a leftover 2 bits. So we add another 0 to it. So, um, so the 3-bit representation for the fractional part is 110, 010, and again 010. Next, we replace these 3 bits by their octal equivalents. That is 101 is 5, 000 is 0, 101 is again 5, 001 is 1, and 110 is 6, 010 is 2, and here also it is 2. And reading this number from the left, we have 5051.622, and this is the octal equivalent. Similarly, for conversion from octal to hexadecimal, first convert the octal to binary by replacing each octal digit by its 3-bit binary equivalent. Then this binary is converted to hex after forming groups of 4. Consider this example. We shall see the conversion of the octal number 5760.1423 to its hexadecimal counterpart. So for this, first we convert the octal number to its 3-bit binary counterpart. So 5 becomes 101, 7 is 111, 6 is 110, 0 is 000, 1 is 001, 4 is 100, 2 is 010, and 3 is 011. You can refer to the previous tables for this conversion. Joining the 3-bit binary equivalents, you get the binary number as this. Next, you have to convert this binary number to hex. For that, you start grouping this number from point into groups of 4 like this. For the fractional parts, you start dividing the binary number from the binary point towards the right like this. So these are the 4-bit nibbles obtained from the above step. That is 1011, 1111, followed by 4 zeros, then 0011, 0001, 0011. Next, we convert these 4-bit groups into their corresponding hexadecimal. So you get BF0.313. Already we had discussed a table for converting this. You can refer to that for this conversion. So the hexadecimal number obtained is BF0.313. Here are some problems you can practice. Please try these out to check what you have learned. These are the key takeaways from today's lesson. To convert to decimal, multiply each digit by corresponding place value and take the sum. Then, to convert a given decimal number, divide the integer part with the new base and collect the remainders in the reverse order. Then, multiply the decimal part by the new base and collect the integer part of the result in normal order. Then, for conversion from hex to octal and vice versa, use the binary number system as the bridge. Thank you for listening to this video. If you like the content, please give a like and share it with your friends. And for more content like this, please subscribe the channel. Thank you.